Okay, we're going to continue on chapter 7. We'll go with that. So last time we were talked about reactions and different ways to classify reactions. So as we talked about last time, there's really sort of two major sort of categories of reactions where, again, more specific classifications could also be done. Really, one big category of reactions are redox reactions. And remember that redox reactions are really oxidation and reduction reactions. And that's really a transfer of electrons is sort of what is happening here. And when we have a redox reaction that occurs, oxidation means that it has basically lost electrons. And somebody that goes through reduction has gained electrons. The result of that, as we talked about, is really a change in its oxidation state, or really kind of like the charge. You can think about it as you go from the left-hand side of the arrow to the right-hand side of the arrow when you look at a particular element. And as we talked about, a really sort of straightforward or simple way to figure out sort of what is being oxidized and what is being reduced is to just use a basic number line. And the idea behind this is, as we talked about, when somebody loses electrons, they then have more protons than electrons, so they're going to become more positive than they started out as. And when somebody gains electrons, they then will have more electrons than protons, so they'll kind of become more negative than how they started. So just by knowing which way we're kind of moving on this number line, even if it's a small movement one way or the other, if it's becoming more positive, that substance is going through oxidation. And if it's becoming more negative, that guy is going through reduction here. And that's sort of, again, the big category of classification. And as we talked about, one of the three reasons why a reaction takes place is really a transfer of electrons. So redox reactions basically take care of that reason as to why a particular reaction will take place, as there is some type of electrons being transferred. Now, more specific classifications of redox reactions are the other sort of ones that we saw, like a synthesis reaction falls under there, or a combination. And that is, again, when we take a couple of things and make one thing. A decomposition, which is kind of the opposite of a combination reaction. That's when we take one thing and really break it apart into, say, a couple of things or so. Also, a single replacement reaction. Where we have one thing that has no charge and an ionic compound. And remember that if it is a metal, it will come in and replace the positive guy and make a new ionic compound. And that guy will come out with no charge on the other side. We could also do that with a non-metal as well, the non-metal coming in to replace the negatively charged one. And the last sort of more specific classification that kind of falls under redox is the combustion reaction. There's really two types of combustion reactions. There's the sort of organic combustion reaction, where you have an organic molecule like something that has carbon, hydrogen, or oxygen, O2, and it will always make really CO2 and water. But remember that really the basic definition of some type of combustion reaction, pretty much all you need is really the presence of O2 on the left-hand side of the arrow, and it can be considered a combustion reaction. So in all these more specific classifications of reactions, what ultimately is still going on is that transfer of electrons, the oxidation and reduction reaction is taking place. And again, those things always happen together. So as we talked about last time, if you could sort of figure out what is being oxidized, by default, the other thing should be reduced. So, if you just figure out one, the other guy has to be doing the opposite thing. The other sort of big umbrella of classifications is double displacement reactions. And in a double displacement reaction, the way that we can recognize it is you will have two ionic compounds, a positive and negative guy on each there. And what always happens in a double displacement reaction is essentially these two positive guys will switch partners on the other side. So on this side, we'll have an A and a D coming together, and a C and a B coming together here. Now, double displacement reactions really take care of the other two reasons why a reaction takes place, which is the formation of a solid. So as these ions are swapping places, one of these products may make a precipitate or a solid. And that is what is known as a precipitation reaction, where on the product side, you get some type of solid that is formed. In addition, you could definitely see that, but acid-base reactions or acid-base neutralization reactions, where you take an acid plus a base and you make a salt plus water. It is the formation of water, which again is the other reason why a reaction takes place. Probably can't see perhaps the water being formed as you could a solid, but that formation of water is again a reason why it takes place. Also a reminder that none of the guys on the right-hand side there have anything to do with redox. There is no electrons being transferred, so everybody stays the same from left to right in terms of their charges. It's just these guys over here on the left-hand side, again, that also have those electrons being transferred. We then got into really two kind of important conversion factors that we use a lot. One maybe more than the other, and that was Avogadro's number. And Avogadro's number is 1 mole of anything is equal to 6.022 times 10 to the 23. And these could be atoms. Remember, they could also be, for example, molecules. It could really be any unit you want on that side. And this is typically the conversion factor that we could write two of them. 1 mole is 6.022 times 10 to the 23 atoms. Or you can flip it around, 6.022 times 10 to the 23 atoms over 1 mole. This is the conversion factor to go really between moles and atoms or molecules, depending, and backwards. So if there is a mention, as we talked about last time, of anything to do with atoms or molecules in the problem, either they give you a number that's in those units or you're asked to solve for a number in those units, then you should use Avogadro's number. Again, if there is no mention of atoms, molecules, or anything like that, you definitely should leave Avogadro's number on the side and not use it. The conversion that we use the most really in chemistry, I would say, is the molar mass. And the molar mass has units of grams per mole. We get that from the periodic table. It is the number that's on the bottom. And typically speaking, we take about 4 significant figures when we take that number off the periodic table. And that is really the conversion factor that allows us to go from grams to moles and backwards. So moles back to grams. So for example, hydrogen has a molar mass of 1.008 grams per mole. You could also use it as dimensional analysis, and as a conversion factor, a mole would be 1.008 grams. If you were going to get the molar mass of a molecule or a compound with many different elements, you basically just add up all the parts. So you add up all the elements, all the molar masses from the periodic table. The relationship between all these two guys, as we talked about, is, for example, there are 1.008 grams of hydrogen and a mole of hydrogen, and a mole of hydrogen would have 6.022 times 10 to the 23 atoms of hydrogen. The moles is really, if you want to think about it, we have basically atoms or molecules in grams. It's really the mole that sort of ties those two things together. And as we go this way or this way, that is Avogadro's number. And as we go this way or this way, That is the molar mass from the periodic table as to where we get it from. Any questions on any of that stuff? I think we talked about it last time, I think. All right, so I believe we were right in the middle of a couple of examples when we laid it up there that you were going to finish at home. Hopefully. Not sure that's instilling a lot of confidence or not. But just in case, why don't you take a few minutes just to look over your work and make sure it all looks good. All right, so let's try these two here and see what. Okay, let's take a look, see how we're doing on these or how you did, hopefully. All right, so the first one is we want to know what is the number of moles and molecules in 55.5 grams of C6H12O6. So first off, do I need to use Avogadro's number at some point in this one? I do. Again, we're looking for molecules, so that's the big thing to know. We're also looking for moles in this case, which we need to kind of go on our route there. So our pathway here is we do have grams to start with. Probably should take those to moles, and then probably should take that to molecules. A reminder as well that when you do see MOL, that is moles, not molecules. So try not to get that confused. So what allows us to do is what we just talked about, to go from grams to moles. That is going to be the molar mass from the periodic table. To go from moles to our molecules, that's going to be our Avogadro's number at that point. So that's sort of our pathway to kind of get to the end. In order to do that, we obviously need to calculate the molar mass of this particular compound. And we basically would go to the periodic table, as these would not probably be provided for you. And once again, we could find the molar mass on the bottom, or these numbers here. And when we have something that's multiple things together, we basically just add up all the parts that are there. So this guy here has 6 carbons, each at 12.01 grams per mole. Has 12 hydrogens, each at 1.008 grams per mole. Again, this is coming from the periodic table, these numbers. And we have 6 oxygens, which are each 16 grams per mole. We basically want to add all that together, and that will give us our molar mass of this compound. Let's say $1.80, but let's see here, 12.01 plus 12 times 1.008 and 6 times 16. Not bad. Good memory, I guess. 180.2 grams per mole is the molar mass of this particular compound. Any questions on how I got that there? Yeah.
The answer, the 180.2, are we supposed to put into the 6?
Yeah, so I was saying in terms of molar mass, both when you take it off the table and usually when you kind of get the final molar mass of a compound, usually 4 significant figures is just sort of what you take it to. So that's why we kind of went to that. So we usually won't follow perhaps the the strict significant figures with this, as it's just a common sort of practice, the 4 significant figures. Other questions? Okay. Remember that this is really our conversion factor for this part right here to get us from grams to moles. And again, we can set it up like dimensional analysis and a conversion factor. We basically got 180.2 grams over a mole of our C6H12O6. Or a mole of C6H12O6 is 180.2 grams. Remember that the number always stays with the grams part, and it's always 1 mole. And I think we might have mentioned it last time, but just a reminder as well that whenever you calculate the molar mass, it's only based off of the formula by itself. So just one of the formulas by itself. That's why it's per 1 mole. So in equations, if there happens to be numbers in front of it or something like that, we only look at just the formula to calculate the molar mass when you do it. By setting it up and using it more as a conversion factor, again, we could hopefully avoid some mistakes in our calculations. So we could start with our 55.5 grams of our C6H12O6. And once again, we really don't have to think about it other than opposites cancel, right? So we want to pick the right one, and that's going to be this one in this case to do that. And that would get us 180.2 grams per mole of our C6H12O6. If I stop right now, the grams will cancel and that will give me moles. So I am going to get an answer in this case because that was one of the questions. Obviously, what is the number of moles? If it wasn't a question, you could continue on to molecules at this point without getting an answer, or you could get an answer. I would say if you're going to continue on to get to the molecules part, try not to round too much. Yeah, if you're going to get an answer and kind of take it. But here I'm going to do a little bit of rounding, but as I continue on, I'm going to use the whole number again, because we're looking for an answer here in this particular case, 180.2. So again, we're basically dividing 55.5 by the 180.2, and that will get us 0.308 moles of our C6H12O6 in this case. Any questions on that so far? Now that I have it in moles, I'm going to now use Avogadro's number here to take it the rest of the way to my molecules. And again, we're going to use our normal sort of Avogadro's number conversions. We have our 6.022 times 10 to the 23. These would be molecules in this case because we're dealing with a molecule over a mole. A mole is 6.022 times 10 to the 23 molecules. So I'm just going to borrow what I boxed there and we're going to continue on. So once again, we can see that the moles are here up on top. So we do want to put the moles on the bottom, which means we do need to go opposite and use the conversion factor like so. And that would get us 6.022 times 10 to the 23 molecules per mole. And the moles will cancel. I won't put a line through it, but I'll put it kind of underneath it there. And once again here, I'm actually just going to continue on with the whole number in my calculator rather than using the rounded number here. So I'm going to times it by 6.022 to the 23. And that will get me, I'll go underneath here, 1.85 times 10 to the 23 molecules. We'll borrow a box there as well. Really, for each of these answers, 3 significant figures based off of the original number there is why we ended with 3. Any questions on any of those calculations there? Yeah. Yeah. For the molar mass you're talking about? Yeah. Yeah, so just in general, as I was saying earlier, pretty much whenever we take the molar mass either from the periodic table and then the individual numbers, underneath elements from the periodic table, and usually when you just kind of calculate it as a whole for the compound, the kind of general rule that everybody follows is usually 4 significant figures. So that's why we go to 4 significant figures. Yeah. Are you talking here? Yeah. Well, in this case, it's just the units that cancel because when we get their answer, it's because we divided the 55.5 by the 180.2. But it's basically what we have is, let me go back this way. We basically have grams on top and we have basically grams on the bottom. So unit wise, what we're doing is basically taking grams divided by grams. So that's how the units basically cancel out to 1. Just like if you were dividing like 2 divided by 2 would give you 1. So that's how the units cancel there. And the numbers don't really necessarily cancel, but they do divide into each other. And that's how we got our answer of 0.308 in that case. Yeah. And that's the same thing that happened here on this end. The moles here do cancel out the moles here. I just didn't put a line through it because it was one of the answers, but those units cancel. And that leaves us really, if we go all the way through here, these grams cancel. These moles cancel. And we're left basically with molecules at the end for our last answer that we're looking for. Other questions? Okay. Looking at the next one there, I scribbled on it, I think. We want to know how many moles and grams are there in 5.25 times 10 to the 14 molecules of CO2. Do I need Avogadro number on this one? I do. Again, we're actually starting with molecules. So we're actually going to go backwards on this one like we did on the first one. Our pathway here is actually we have molecules. And we want to end with moles and then grams. So again, it's that Avogadro's number that allows us to do that conversion. And our molar mass there from the periodic table is going to allow us to get from that moles to grams in this particular case. So once again, I do know down the road there at the end, I'm going to need the molar mass of CO2. So I'm going to calculate that up front so I have it available to me. So CO2, once again, we're going to go to the periodic table. And in this case, we have just one carbon. So that's 12.01 grams per mole. That is that number on the bottom. There are 2 oxygens in this case, and each of them would be 16 grams per mole. And 4401, I'm going to go with off the top of my head there. And that's going to be our molar mass here of CO2, which we're going to use at the end here, again, as a conversion factor to take us basically to the end of our calculation. But the first part of the calculation can be done simply, again, using Avogadro's number as our conversion factor. So we will start with the moles there, our molecules. So we got 5.25 times 10 to the 14 molecules of CO2. Once again, and I'm just going to steal the guys that are up there. We want molecules in this case on the bottom. So we actually want to use it in this form, the one in the box there. Yeah. Everybody get the alert earlier today, and my lab just lit up with like sound. Oh my God. Jeez. All right. So we got a mole on top. We're going to put Avogadro's number there on the bottom. And we're going to put our molecules there on the bottom. And that's going to, again, cancel out our molecules. And once again, if we weren't really looking to solve for moles, we could just continue on with the calculation if you want, or you could also get an answer. But since we do want the answer here, we're going to take our, and again, we're basically dividing at this point. We're going to take our 5.25, make sure we use our exponent button, hit 14. We're going to divide it by 6.022. We also want to make sure we hit our exponent button there. And in this case, once again, I'm going to round because we do want an answer 8.7, looks like 2 on my calculator, times 10 to the minus 10 moles of CO2 in this case. Any questions on that part there? Now that we do have it in moles, we really can take it the rest of the way there. And now we're going to use the molar mass that we calculated earlier as really a conversion factor to do that. And I clearly am out of room on this point. I'm going to go backwards a page, I think, and continue on. Everybody good? Yeah. All right, so to continue on here, maybe it's a fresh page. I'll get rid of all my scribble here. Yeah. All right, so we're sitting right now with 8.72 times 10 to the minus 10 moles of CO2. Earlier, we calculated the molar mass of CO2, which is basically 4401 grams per mole of CO2, or a mole of CO2 is 44.01 grams. So again, we're going to use this to get us to grams. And by setting it up like this, all we have to do is opposite. So our moles are up on top. So that makes the selection fairly simple for us. We're going to take the guy on the left there where our moles are on the bottom. So 4401 grams per mole of CO2. The moles of CO2 here are going to cancel. And I still have the whole number in my calculator, so I'm just going to continue on with that one, which is 4401. And whoa, I picked a weird number there. All right, I'm going to do a little scientific notation. It feels like a lot of zeros there on my calculator. We're going to end up with maybe something like 3.84 times 10 to the minus 8 grams of CO2 in this particular case. If your calculator is not in scientific notation, you may have a bunch of zeros and a 3 and an 8 at the end of your calculator as it ran out of room towards the end there. Any questions on either of those calculations there? So clearly you need to be able to obviously calculate any of those things: grams, moles, grams, molecules, atoms. As I mentioned before, pretty much molar mass is going to be probably the one you go to the most. And again, you just get that from the periodic table. Any questions? All right, so before we move off from this, let's talk about one other type of sort of problem that sometimes comes about when we're kind of doing these types of conversions. And I think maybe I'll use here, that'll work. So let's say we had, I don't know, let's say we had 62.5 grams of C2H4. And we want to know how many hydrogen atoms is that? So in this particular problem, we got a couple of things going on. First off, should I use Avogadro's number? I should, because I'm looking for atoms. But I'm looking for atoms of only what? Hydrogen, right? Not the whole thing. So sometimes you do get questions like that, like, how many grams of just carbon, or how many atoms of carbon, how many moles of hydrogen that there may be. And sometimes you may not be interested in the entire thing. So there is a way that you could actually use the formula to allow you to kind of convert from like the whole thing to just like one part of it, one of the elements that are there. So if we look at this formula, for example, which is C2H4, these numbers on the bottom can be considered the moles of each of these guys. And basically, we could come up with a conversion factor that uses the formula to allow us to go from the whole thing to just like hydrogen or carbon. So for example, we could say in this case that for every 1 mole of the entire thing here, we would have how many moles of just carbon? It would be just 2, which is that number there. So that would be 2 moles of carbon. We could also say in 1 mole of the entire thing, there would be how many moles of hydrogen in this case? There would be 4 moles of just hydrogen. And from each of these equalities, we could really write 2 conversion factors. So we could write, for example, 1 mole of C2H4 is 2 moles of carbon, are 2 moles of carbon, and 1 mole of the entire thing. For the other one here, we could write 1 mole of the entire thing gets me 4 moles of hydrogen. Our 4 moles of hydrogen gets me 1 mole of the entire thing. So we could actually, from the actual formula itself, come up with 4 usable conversion factors that will allow you really to go both ways. You could go from the whole thing to each element. You could actually go from each element back to the whole thing. And to do that, first off, any question on how I got those relationships? Now, the important part of this is those relationships are in what units? They're moles, which means I can't use them unless my other number there is in moles. So before I could use those to go from the whole thing to the individual elements, I got to get them in the right units so everything cancels out. So we are going to start kind of like normal here. We got grams and really we want to take it to moles. So to do that, we would need to go to the periodic table and get the molar mass of this particular compound. And if we went to the periodic table, we would see carbon is 12.01 and we would see hydrogen there is 1.008. So just like before, we're just going to add up all the parts. There are 2 carbons. And there are 4 hydrogens. And this gets me 2 times 12.01 plus 4 times 1.008. Going to give me a molar mass of 28.05 grams per mole. So that's the first step that we're going to do. We're going to use that molar mass as a conversion factor. So we're going to take 62.5 grams of the whole thing here, using the molar mass that we just calculated. The units that should go on the bottom in this case, moles or grams? Grams. So the number stays with the grams, so that needs to go on the bottom. And the moles of the whole thing here will go up on top. The grams of the whole thing now cancel out. Any questions on that? Yeah. You should probably put at least, like I did there, at least the formula in one part of it, either the grams or the moles part, so that you know what it is as you're doing the calculation. Yeah. Other questions? All right, so in this case, I'm not going to get an answer at this point because I want to kind of go to what we're really looking for here. So now that I have it in moles of the whole thing, I can now take it to moles of what I'm looking for. And in this case, I'm looking for just hydrogen, right? So what conversion factor here should I use? The one on the right or the one on the left that involves hydrogen? Should I use this one on the left or this one on the right? Which one is going to get rid of the whole thing and leave me just hydrogen? The one on the right will do it. It is still opposites, right? So I got moles of the whole thing up on top. So I want to use moles of the whole thing on the bottom. At this point, the moles of the whole thing will cancel out, and using the formula, it has allowed us to get to just hydrogen. First off, any questions on that? Is this the answer, by the way? The units I'm in right now are moles of hydrogen, but I want atoms of hydrogen. So how do I go from moles of hydrogen to atoms of hydrogen? I need to use Avogadro's number. So here to finish it out, we're going to use Avogadro's number to take us to that last step. And I'm going to erase some of this since I obviously ran my calculation into those conversion factors. So I'm going to get rid of some of that there. All right, so now that we got it to moles of hydrogen, we will use Avogadro's number, which once again is 1 mole of anything, right, is 6.022 times 10 to the 23 atoms. So following our logic, the unit that we have left right now is moles of hydrogen on top. So on the bottom should go atoms or moles? The bottom should go moles. So on the bottom should go a mole of hydrogen. Gets us 6.022 times 10 to the 23 atoms of hydrogen. At that point, the moles of hydrogen cancel. Just put it into our calculator at this point, right? So we're going to multiply all the way across, and we're going to come back and divide in this case, right? So if we do that, that's going to get us 62.5 times 4 times 6.022 to the 23. And I'm going to hit equals at the time I'm done with the top. I'm going to divide it by 28.05 and hit equals. And that is going to give me that in this particular compound, there is about 5.37 times 10 to the 24 atoms of hydrogen. So sometimes, like I said, you may not be interested in the whole sort of compound. You may be interested in one of the elements in the compound, and you can use the actual formula as a conversion factor, a kind of mole to mole conversion factor to allow you to go from the whole thing to each individual element. Any questions on that calculation? Or moles, Avogadro's number, molar mass? Any questions on that? So now that we can do our conversions here using molar mass and Avogadro's number, I guess, as well. And earlier in this chapter, we talked about balancing equations. We're going to actually put both of these things together And we're going to actually do some calculations from equations, which is known as stoichiometry, which kind of puts both of those things together, the balancing of equations and sort of the grams to moles and molar mass sort of relationship. So let's take a look at that. So calculations from the equations, which is known as stoichiometry. And stoichiometry really takes advantage of a balanced equation. And as we'll talk about many times, pretty much all stoichiometry calculations, if your equation is not balanced, you're kind of wasting your time. So it always needs to be a balanced equation to do these type of problems. And when we look at a balanced equation, there's different ways that we could look at, say, the coefficients that we see in the equation. One way here, we could look at these numbers and consider them molecules in this case, since all these guys are molecules. So that would be 2 molecules of H2 react with 1 molecule of O2 to give us 2 molecules of H2O. The relationship that we use pretty much in stoichiometry is actually this middle relationship here, and is what is sometimes referred to as the mole to mole relationship. And we can see from the equation 2 moles of hydrogen reacts with 1 mole of oxygen to give us 2 moles of H2O. These numbers come from just the coefficients. Yeah, so that is where those numbers come from. They match up, right? 2 and a 2, a 1 basically and a 1, a 2 and a 2. So that is where those numbers come from, just the balanced equation. And that's also why obviously it's important to always make sure your equation is balanced. The last one is conservation of mass. We have 36 grams of reactants. We should get 36 grams of products. So when we use this mole to mole relationship, what it allows us to sort of figure out are questions like, if we throw into this equation so much reactants, how much products we should make, right? And we could also go the other way around. If we get out of this reaction so much products produced, we could actually back calculate using stoichiometry to figure out how much reactants we actually put in there. So we could actually even stay on the same side of the arrow and go, if I put this much of this reactant, how much of the other reactant do I need to put in there? And the same thing on the right-hand side of the arrow. If you know how much of one product you make and you have another one, you can figure out how much of the other product you will make as well. So it allows us to do calculations where we could really figure out pretty much anything in the equation, how much you produced, how much you started with, how much you need of the other reactant to put in there. And these type of calculations help us do that. So the units that you could use in stoichiometry calculation can really be any units, but I'll be honest with you, for us, we're really not going to do stoichiometry involving gases or solutions or any of the other stoichiometry stuff. We're going to stick to this basic sort of grams and moles. So for us, these will really be the units that we will see mostly in these stoichiometry problems. And this is why molar mass that we were just talking about is really important, because that is, again, our conversion factor to go between grams and moles to grams, the molar mass from the periodic table. So that conversion that we were just doing with the molar mass is really important because it's used a lot in stoichiometry. It frankly is usually the first step that you do when you're doing some type of stoichiometry problem, is to take the grams that they give you and basically convert them to moles. So the mole method is based on the idea that the coefficients represent the moles of everybody in that reaction or that equation. And you could kind of have a mole to mole sort of relationship of how they react. So there are some steps that you follow when you do stoichiometry problem. There's actually an extra step on here that you might not come across a lot, but it is possible that you could have a problem where they give you everything in words. And to start a stoichiometry problem, you need a balanced equation. So if you happen to be given everything in words and not an equation, just words, you need to write the correct formulas first and then balance the equation, which is the second thing that you want to do there. I would say probably 99 times out of 100 in this class, you will have the equation given to you. So you could just start with the balancing equation part of it. But sometimes you may have one that's all words. You got to kind of write the equation first. So you want to do the right formulas based on nomenclature and then balance the equation. The next thing that you want to do is take whatever they gave you and whatever unit it is, and you need to get it to moles. So that may just be grams to moles using the molar mass. You may have pounds, where maybe you got to go from pounds to grams to moles, whatever unit may be. But probably in a lot of cases, it will most likely be grams and using the molar mass to get to moles. But it could be multiple sort of calculations. But pretty much whatever piece of information they give you in that problem, get it to moles. And usually is the last step there is grams to moles using the molar mass. So usually this step right here is usually your grams to moles using your molar mass to do so. The reason you have to do that is because of the coefficients are mole to mole relationships. So just like we saw in that last problem we did, we have to get everybody into the right units. So we have to get everybody into moles so that we could use the equation and that relationship to go from one thing in the equation to something else. So the purpose of stoichiometry sort of calculations is you are oftentimes given something in the equation that you're maybe not interested in, but you want to know about somebody else in the equation. So you need a way to go from like the reactant here to the product over there. And it's really a conversion factor. What stoichiometry is, people freak out about it and go, it sounds like a big word, but it's really just a conversion factor. And instead of looking up the conversion in a table, where you get the conversion from is the balanced equation. So that's why it's really important that the equation is balanced. And you'll find really the two things that you're interested in, and you'll do the mole to mole relationship, which we'll talk about in just a second, but it's basically just those coefficients. And what that's going to do is allow you to go from whatever they gave you to what you're really interested in. So that's going to allow you to do that conversion. Once you do that, you will end up with moles of what you're looking for. And if that is actually what you're looking for in terms of units, you can put a box around it. But you may have to usually do one more conversion at the end. So maybe you want grams at the end. So a lot of times on the back end of the calculation, you'll use molar mass one more time to go from moles back to gram. So pretty much for our purposes here, you could kind of eliminate one of these steps. And pretty much there's 4 basic steps to these problems. You want to always start with a balanced equation. You want to convert to moles. Which usually involves the molar mass. You want to do the mole to mole relationship from the equation. And then at that point, you should always be in moles. So a lot of times you want to convert the moles to some other unit, which also will sometimes mean the molar mass on the back end. Pretty much these are the 4 steps that you should always follow, and just go in order, and it will get you to the end in the right process. And if something is done for you, you just skip a step and go to the next step. Don't go backwards. I've seen people go backwards, like unconvert things, because like I have to get it to moles, but it's already in moles. Let me take it back to grams and back to moles and go backwards. So you don't want to do that. You just want to follow these basic 4 steps, which up here is basically steps 2 through 5 is basically what I just wrote up there. All right, so let's take a look at an equation here and sort of see our relationships that we can kind of get from an equation and what we could kind of do with those. So let's take a look here at this particular equation. So from this one equation, first off, you definitely want to make sure it's balanced before you begin. If we take a quick look at it, we got a couple of carbons, we got a couple or 4 oxygens on each side, so it is balanced. So from this one equation, there's a lot of stoichiometry or stoichiometric relationships that we could get. We could say simply looking, and there's no crazy math here at this point, it is just the coefficients from the balanced equation. So we could look at those coefficients and say, for every 2 moles of CO that I toss in there, I should get out how many moles of O2 in this case? What's the coefficient in front of it? 1. Coefficient is 1, right? If there's nothing written there, it is 1. So I will get 1 mole of O2 out, and that is just simply the coefficients from the balanced equation. Also, if I throw in there 2 moles of CO, how many moles of CO2 would I get out? 2 moles of CO2. Once again, it is just the coefficient. If I throw in there 1 mole of O2, how many moles of CO2 will I get out? I will get out 2 moles of CO2. From this one equation, we have these three equalities, and they are equal to each other. So let's just make sure everybody understands they are clearly not equal to each other in terms of numbers. So I believe 2 and 1 still does not equal each other, I hope, right? So 2 and 1 doesn't equal each other, but they are equal to each other in terms of proportion. Like this is what you need to throw in there to produce product, a certain amount of product. It's kind of like when you make cookies, right? You need so much flour, right? So much chocolate chips, maybe a little bit more chocolate chips, right? To get a dozen cookies to come out, right? How big you make those cookies, right? But it's sort of the proportion. You got to put everything together to sort of yield yourself maybe a dozen cookies, 2 dozen cookies, 3 dozen if you make really small cookies, I suppose, right? So, but that is what the stoichiometry is here, is basically the proportion that we need to kind of put into this reaction of each of these reactants to sort of produce a certain amount of products at the end of it. Any questions on that? Now, because these are technically equalities, we could actually write 2 conversion factors for each of them. So for the first one, we could write that there are 2 moles of CO over 1 mole of O2. We could do the opposite, 1 mole of O2 over 2 moles of CO. For the second one here, we could write 2 moles of CO over 2 moles of CO2 are 2 moles of CO2 over 2 moles of CO. And lastly, here for the third one, we could write 2 conversion factors, 1 mole of O2 over 2 moles of CO2 are 2 moles of CO2 over 1 mole of O2. So from this one balanced equation, we just got ourselves 6 different conversion factors that we could use. So from each of these stoichiometric equalities, we could get these conversion factors. Now, the good news is you're not going to use them all in a problem. Otherwise, that problem is just going to end up back to 1 where it started. We're actually going to probably use one of these conversion factors in a problem. You just need to pick the right one. And again, if you set things up like we've been doing, you want to choose opposites to basically get rid of the unit you don't want and end up with the unit that you do want. The purpose of this is, again, we will be given something in this problem and we're not really interested in it, but we're interested in somebody else. So there is no table where I could look up and go like CO2 and CO, what is the relationship between them? So we find the conversion factor from the actual balance equation. Any questions on that? So why don't we kind of run through the 4 steps here and see how we could use this. So let's say, for example, we produced we'll go with 125 grams of CO2 in this reaction. How many grams of, let's go with O2, did we start with? So obviously you could get all these equalities, you get all these conversion factors from this problem, but we want to think about this as being a stoichiometry problem, and we want to follow our sort of steps. So the very first step that we talked about is you want to make sure that you have a balanced equation, right? And in this case, we do, obviously. So that is the first thing that you want to do whenever you see the equation. Even if there are numbers in it, you might want to take a peek at it and make sure it is balanced. It probably is. And definitely, if you do not see numbers, you should take a pretty good look at it to make sure that it is not balanced, or if it isn't balanced yet, you're able to balance it. Next thing we want to do on our journey here is to take whatever they gave us and convert it to moles. So in this case, I was given 125 grams of CO2. Do I need to convert that to moles in this case? I do, right? And to convert it to moles, that's going to be the grams to moles conversion. And we actually did it earlier, right? That means that I would have to go to the periodic table and calculate the molar mass of CO2. I think we did on that problem, the second problem that we did earlier. So if it's okay with you, I'm just going to steal the number that we did there earlier for the molar mass. And if you went to the periodic table, you would add up the 22, not the 22, the 12.01 grams per mole plus the 2 times the 16. And that gives us our 44.01 grams per mole for CO2. And again, we calculated that in the previous problem. And again, you would go to the periodic table to do that. We're going to use this as our conversion factor, just like we did there. So we're just going to simply take this from grams to moles. So that is what we want to do in our second step here. We're going to take 125 grams of CO2. So I want to get rid of grams and end up with moles. So what should go on the bottom here? The grams. In this case, that would be 4401 grams per mole of CO2. That comes from the periodic table and the molar mass, just like we did on that previous problem. So I am going to get an answer here. Why not? 125 divided by 44.01. I got something like 2.84026. I'm going to take it to a few digits because I'm not done with the problem. So I still have a little bit more to go. So I'm not going to do a lot of rounding at this point. But these are moles of CO2. So that is definitely the second step that you should always do. Take whatever they gave you, convert it to moles. Any questions on that? Now, if we think about where we are in the equation, we want to do step number 3, which is find the mole to mole relationship from the equation. So the two things you're interested in is obviously whatever they gave you. So in this case, that is CO2 they gave us, right? So we're definitely interested in that. We ultimately want to find the grams of O2, which means we are interested in that, right? So those are the two things in this problem that we're interested in. They gave us CO2 and we want to end up at O2. This is what we need stoichiometry for, and this is what the third step is for our conversion factor. So we did this earlier. We saw that for every 1 mole of O2, we get out 2 moles of CO2, which gives us our options of conversion factors being these two right here, yeah? Which one should I use? The one on the left or one on the right? I'm going to continue on with my same number, which is moles of CO2. And I think I heard left, right. Which one in this case? It is going to actually be the one on the left because we actually want to get rid of the CO2 and we want to end up with the O2. So we would use this one just like a normal sort of conversion factor, opposites. That's going to put us 1 mole of O2, gives us 2 moles of CO2. That comes from the balanced equation. And don't blink your eyes, but that is the big stoichiometry move right there. Yeah, this is basically just a conversion. Yeah? So we're going to basically take the number that I got going on there, and we're going to divide by 2. And that's going to give me 1.4201 moles of O2. Any questions up to there? Yeah. Why did we choose the one I circled? Is that what you're asking?
Yeah. Why did you choose it?
We chose the third one because that has the 2 things that we're interested in. So you're always interested in whatever they gave you. So in this case, it gave us CO2, right? Some information about that. And the other thing that you're interested in is what you're trying to find. And in this case, we're trying to find O2, right? So that is the 2 things that we're interested in. We're not interested in like in the middle one. We have no interest in CO, so no need to use it. And like the top one, we have no interest in CO either. So that's not going to help us. So the only relationship that will help us is that one that's on the bottom. Other questions? Am I done with the problem, by the way? No, I'm close to the units I want, right? I'm in moles of O2, which is not what I want. I actually want grams. So the last step that we need to do is to take whatever they have and take those moles to the units we're looking for. So now that I have moles, How do I get back to grams? I need and what do I need the molar mass of in this case? Of oxygen. It's no longer CO2, right? Because we just did that conversion. So we have to go back to the periodic table and figure out the molar mass of O2. And for O2, it is 2 times 16, which is 32 grams per mole. So our last step here, we want to go opposite. So we're going to put the moles of O2 on the bottom, 32 grams of O2 up on top. The moles of O2 will cancel. And at this point, we're going to multiply by 32. And at this point, I'm going to clean it up to right sig fig since we're at the end. That is going to be 45.4 grams of O2. And that is 3 significant figures based off of the only number in the problem, which is 3 significant figures. And everything we did was multiply and divide. These are all the same 4 steps that you should follow exactly like that. Yes, and that will get you to the right answer. So let's take a look. Let's take a look at maybe another equation just to make sure we all understand where all of those relationships come from. So what I'm scrolling through there, we'll do here, perfect. So let's take a look at this equation here. Let's say we had, H, let's get something to write with this, not a highlighter. Let's try that maybe. There we go. Okay, so let's say we got H2 plus N2 makes a little NH3. Do a balancing there. Actually, no. All right. So what I would like you to do is I would like you to balance this equation, right? Because that's always what you want to do. So if you think it's balanced, go with it. If not, maybe balance it. And then I want you to write all of the stoichiometric equalities that you could get from this equation and all of the conversion factors that you could get. So all the conversion factors and all the equalities that you could get from this equation. And again, I would probably balance it first. Yeah, so make sure that you balance it up. So make sure everybody's clear on where we get all of these guys from. Okay, let's see how we're doing. So obviously, definitely when we're doing stoichiometry problems, you got to have that equation balanced. Again, pretty much your calculator is going to be completely wrong in most cases, unless you happen to get like a 1-to-1, everybody's ones by some chance. But it's going to be wrong if you don't balance it. So again, it's really important to make sure that you do that. This goes back to what we were talking about when we were balancing equations. Again, if you want to, you can make a table, reactant side, product side. We got hydrogen, we got nitrogen. On the left-hand side there, we have 2 hydrogens, which would be the number on the bottom. On the right-hand side there, we do have 3 hydrogens. Left-hand side, we have 2 nitrogens. Right-hand side, as we were just talking about, nothing written there. So we do have 1. So in this case, not a lot to work with, but perhaps the nitrogen would be the easiest to solve. We could put a 2 in front of it. And when we put a 2 in front of it, again, that 2 does go for everybody that's behind it, right? So you do have to sort of distribute that 2 to everybody back there. So that means that in terms of hydrogen, we now have 6. And in terms of nitrogen, we have 2 at that point, right? So now we got the nitrogen balance. What's left is the hydrogen. And we can simply fix that by putting a 3 here in front of the hydrogen. And that's going to give us, once again, 3 times 2 there, which is 6. And we still have our 2 nitrogens. Yeah. Any questions on the balancing part of the equation there? All right, so now that we have it balanced, we are ready to draw from this, again, all of the stoichiometry or stoichiometric equalities and conversion factors that we could get from this. A reminder, as we've talked about, clearly in a problem, you're not going to use them all, but it's good to know what's available to you so you can pick what you need. And again, really, you could look at this equation as sort of a conversion table for you, right? And this is going to be a specific conversion table for any type of problem that you do that involves this equation. So when we get this stoichiometric mole to mole relationship from the equation, There was an earlier question, and now everybody's back, just to make sure. It is nothing more than just the coefficients in the balance equation. So when we look for those relationships, we're just going to look at the coefficients, which are numbers in front, and there's no magic or calculation that she has to do. Once it's balanced, we're just going to simply use those numbers. Again, a reminder that if there's nothing written there, that represents one of whatever that is. So we're just going to kind of start to the left and go to the right and go to the right again and kind of get everybody together. So for our H2, there are how many moles of H2? 3 moles of H2. And that means that I would have to put how many moles of N2 in there? 1 mole of N2, right? Now, if I also throw in there 3 moles of H2, how many moles of the NH3 should I get out? It should also be 2 moles of the NH3. And lastly, if I throw in there 1 mole of my N2, how many moles of the NH3 should I get out as well? 2 moles of the NH3. So again, this is basically the 3 equalities stoichiometrically that you can have from this balanced equation. Any questions on how we got those? All right, so once again here, you don't necessarily in every problem need to write all these conversion factors, but we could get 2 conversion factors from any equality. And that's really just goes back to the same thing we did when we did 12 inches is 1 foot, right? We could do 1 foot over 12 inches or 12 inches over 1 foot. So we're just going to write the conversion factors that we could get for each of these. So starting with the first one there, we could say there are 3 moles of H2 over 1 mole of N2. Or we could flip it around. 1 mole of N2 gets us 3 moles of H2. For the second one, we could say 3 moles of H2 gets us 2 moles of NH3. Our 2 moles of NH3 gets us 3 moles of H2. And lastly, from our last equality there, we could get 1 mole of N2 gets us 2 moles of NH3. Our 2 moles of NH3 gets us 1 mole of N2. So once again, these are all of our conversion factors. And these are all of our equalities that we could get from this one balanced equation. Any questions on how we got any of those things? Yeah. All right, so now let's use some of these things in a problem. Let's just make up one and do it. Let's go with, why don't we do, what's that? An easy one? What's 1 plus 1? No, I'm just kidding. 4. No, I'm just kidding. So let us do a nice, easy one. I believe in you. So let's say that we threw in there, we threw something in there. Let's say we did 15.5 grams of H2 is reacted in the equation. How many grams of N2 would you need? So I'm going to give you a couple of things. First off, obviously here, we want to follow our 4 steps. So the 4 steps is, again, to balance the equation, to convert to moles, to do the mole to mole relationship from the equation, and lastly, convert moles to some other unit. All right, so you might need here a couple of numbers from the periodic table. Nitrogen 1401, hydrogen 1.008. All right, so give it a go. Follow the steps in the order, and it should end you at a problem at the end that is the right answer. I'll do it as well since I made up the number, so I get to do it. Okay, let's take a look and see how we're doing. So before we got to this problem, we set up our equation. We got a balance. We got all of our basically conversion factors that we could get from the equation to do our stoichiometry. So as I mentioned before, pretty much for our class, all stoichiometry problems will boil down to these 4 steps here. You want to, again, make sure 100% of the time that that equation is balanced. Even if you see numbers, it's a good idea to take a look at it and make sure that it is balanced. Definitely, as I said before, if you don't see numbers, you should take a pretty hard look at it and make sure that either it's balanced or you need to balance it. The next thing we want to do is convert to moles, and that's in our case, whatever information they give us, we want to take whatever unit it is in and get to moles. And again, usually that last step is our grams to moles, like we were doing with our molar mass to get there. We want to use the equation, which is really what stoichiometry is, to do a mole to mole relationship. It is nothing more than really a conversion factor that we get from the equation rather than looking it up in the book or a table. And lastly, if you do steps 1 through 3 correctly, you should be in units of moles. And then you may have to convert it obviously to some other unit, which is the 4th step. So let's take a look at this, and we're going to run through the steps here again, just to make sure. And clearly I wrote a lot on there. So I'm going to make a little room so I could get in there. So we have all of our equalities and we have our conversion factors that we used or can use in this equation. All right, so let us run through this here and see. All right, so first off, we obviously did this to start this problem. We want to make sure everybody understands where we get those equalities from and the conversion factors. So clearly, step number 1 is done for us at this point. We do have a balanced equation. And again, none of it works, right, if you don't have that balanced equation. Next thing we want to do is, we can check that off. We want to go and convert to moles. In this particular problem, do I need to convert to moles? I do, because the only piece of unit that is given to us is in grams, right? So we do have to do step number 2, which is to convert to moles from grams. And to convert to moles, we need to use what? We need to use the molar mass from the periodic table, right? So if we go to the periodic table, maybe your eyes are better than mine, you can see that one, but again, it will look something like that over here. And that number on the bottom is the molar mass for hydrogen. We do have to be careful here. Hydrogen is not just H here, right? But it is H2, right? So we do need the molar mass. And for H2, that would be 2 times our 1.008 grams per mole from the periodic table. And we have 2 times 1.008, going to give us 2.016 grams per mole as our molar mass for H2. Remember that molar mass is what we're going to use as a conversion factor. Yes. Would we be using the N in this at this point? Is that what you're asking? No, we would not, because the only number that was given to us is actually hydrogen, right? So not nitrogen. So we have to really start with the number that was given to us. And in this case, it is just hydrogen. So we got to start there. We eventually want to get to N. So we'll eventually get over to N to use it, because that's ultimately what we're looking for, which is nitrogen. But to begin with, the only unit that we have is hydrogen. So we have to begin there. Another really important thing that we talked about as well is, when we calculate the molar mass, it is based just solely on the formula, right, which is H2. We do not want to take that coefficient into account when we do the molar mass, because we're going to take the coefficient into account when we do the stoichiometry. So you do not want to do it in both places. So as we talked about earlier, regardless of what the number is in front of those formulas, we want to just do the molar mass based off of just the formula. And that is why it is grams per 1 mole, again, because it's just based off the formula. So now that we have everything that we need to do step number 2, let's do it here. So step number 2, we're going to take the only number that was given to us, which is 15.5 grams of H2. We're going to use our molar mass as a conversion factor. And again, you do want to set it up like this, using dimensional analysis as we've been doing, because really it makes the math easy. We just got to remember opposites, right? So I have grams up on top. What should go on the bottom? Grams or moles? Grams should go on the bottom again so that it cancels out. So we'll use our molar mass for our H2, 2.016 grams per mole of H2. At this point, the grams of H2 will cancel each other out. We're going to multiply by 1, basically, if you want to. You don't really need to. Then you're going to come back and divide by 2.016. So we're basically going to divide by that number. And if we get a number here, 15.5 divided by 2.016. And again, I'm going to take it to a number of digits here because I do know that we have a little bit more to go in our calculation here. So I'm not going to do rounding yet. And that will give me moles of H2. Any questions up to that point? So really all we've done at this point is change our units from grams to moles. And the purpose of that really is to set us up for success in step number 3, because we're going to use a mole to mole relationship. So in order for everything to cancel out correctly, we have to get those guys basically into moles. So now we are ready for step number 3, and we want to go to our balanced equation and find the two things we're interested in. And in this case, the two things we're interested in is what they gave us, which in this case would be H2. And the other thing that we're interested in is what we're trying to find. In this case, we're trying to find, as a question earlier, nitrogen, right? So this is where we're going to use nitrogen, the relationship between these two. And I did have to erase it for a little bit of space, but as we had up there earlier, we used the coefficients, and we see that that is 3 moles of H2 give us 1 mole of N2. So that was the one that we had up there earlier. That gave us the two conversion factors that we should look at to help us do this problem. And that was these two conversion factors here. And remember, again, we are in the process of doing the stoichiometry where we're really not interested in H2, but we want to end up at N2. So this is what we're going to use to convert it. So step number 3, we will continue on with our number. 7.68849 moles of H2. So remember, I do want to get rid of H2 and end up with N2. Should I use the conversion factor on the left or the one on the right to do so? We're going to use the one on the right. So again, opposites cancel. So that's going to put the moles of H2 on the bottom so that it will cancel out. That will give me my 3 moles of H2 and my 1 mole of N2. So that is, again, the big stoichiometry step right there, that conversion. And it does come once again from the balanced equation, as our molar mass obviously came from the periodic table that we did previously. So in this case, we're going to basically divide by 3. So I'm taking the whole number I still have on my calculator because I'm not done with the calculation. I'm going to divide by 3. And that's going to give me, we'll go with 2.5628 moles of N2. So we just use stoichiometry really as a conversion factor to go from H2, which is not what we're interested in. Now we're over to N2, which is what we are interested in. Any questions so far? If I wanted the answer in moles, I could clean up the significant figures, right? And now I would have my answer. I could put a box on it. But do I want the answer in moles in this case? I don't. I want the answer in grams. So to go from moles to grams, we need to use molar mass of what at this point? Of the nitrogen. So that's also a very important thing to remember. We're no longer at hydrogen. We have converted over to nitrogen. So we do need to go back to the periodic table and calculate our molar mass of N2 in this case. And once again, we'll grab the number there from the bottom of the box there. Bless you. Bless you. And we'll take 2 times 14.01 grams per mole. And this will give us our molar mass here of our nitrogen. 2 times 14.01, going to give us 28.02 grams per mole as our molar mass of nitrogen. And that is what we're going to use as, again, a conversion factor. So to finish this up, we will do our fourth step here. And step number 4, I'm continuing on with my number from the previous step that I did not round too much. So do I want grams or moles on the bottom here? I do want moles. Again, opposite's going to cancel out. So we will have 28.02 grams of N2 on top and a mole of N2. Once again, the moles of N2 will cancel. We're going to multiply 28.02 by my number I had previously. And at this point, I am going to clean it up since this is our final answer to the right number of significant figures. By the way, the right number of significant figures in this case would be, it would be 3, as this is the only number that we see here, right? So it has 3 significant figures. Pretty much all of these conversions that we did is multiplying and dividing, which means we look at significant figures. So that would be how many significant figures we should have. Yeah. 3. Are you asking what 3 significant figures? It comes from this number, that 15.5, which is really the only number that we see in the problem. And again, all the steps that we did, mathematically speaking, multiplying, dividing, we look at significant figures. So that's what we should end up with, which looks like, you're welcome, on my calculator here, looks like we got a 71.8 grams of N2 would be our final answer in this case. I'm hoping that you can start seeing a pattern that it is those same 4 steps. Yeah, people always don't want to kind of do it, but if you just follow those same 4 steps, you will go down the right path. Now, clearly here in this process, I showed the answer after each step. You don't have to do that. You could just do one big calculation from, step 1 to step 4. Or you can get an answer after each step. Whichever way you prefer is fine with me. A reminder, though, that if you do get an answer after each step, like I did here, I would not round to the very end so that you don't move too far off of the right answer. Other questions on this? So what does this number mean? This number means that if I wanted to do this reaction and I throw in there 15.5 grams of H2, I would have to put in there 71.8 grams of N2 to basically use up all of that H2 that I put in there to get this reaction basically to go like it is. So that is basically what that number basically represents. Yes. How did I get which one now? For step 2? This part here? It's from the molar mass from the periodic table. So remember, when you calculate the molar mass, which we did down here, which is basically, since there's hydrogen is H2, we want to take 2 times the molar mass that we find on the box for hydrogen. And that represents basically 2.016 grams per mole of H2. And you can basically, let me go back here somewhere where I haven't scribbled too much today, too much scribbling. But basically, when we have something like this as our molar mass that we get from the periodic table for something like H2, we could also use it really as a conversion factor. So you could write 2 kind of conversion factors where you basically put the grams up on top and the moles on the bottom, or you could do it the other way around and use it as a conversion factor like so. So it comes from the periodic table and the molar mass, and we basically use it as a conversion factor, kind of similar to what we did a little earlier on in the chapter. Other questions? All right. Okay, so let's take a look at another one here. So you will be professionals here by the time we're done. I believe in you. All right, so we have lithium metal reacts with water to form hydrogen gas and lithium hydroxide. In this case, we're looking for how many moles of H2 can be formed from the reaction of 5.32 moles of lithium with water. And a couple of things that you probably will need is maybe, or maybe not on this one, but I'll put it up anyway, 6.941, hydrogen 1.008, oxygen is 16. All right, so we'll start the first part here together. Before we do this one, we need what to actually start this sort of calculation? We need an equation. So this is what we were talking about earlier, where it wasn't really given to us in formulas. So we want to make sure we write the correct sort of formulas first, and then we could get into the balancing and all that. So lithium metal is Li, reacts with water, which is, that's good. Remember, that's not a trick question when you see H2O. It is water, right, on the test. And the question disappears, which is a good question. Let's take a look at it again. To form, which means we have an arrow, right? Hydrogen gas is, it is H2. So remember, hydrogen gas is a diatomic molecule. You do not want to just use H, otherwise it's going to be a long day trying to balance. Yeah, so nitrogen, oxygen, hydrogen, chlorine, fluorine, bromine, they're all comes as twos as they naturally do. Lithium hydroxide, lithium is Li plus, right? Hydroxide is one of those polyatomic ions, which is OH minus. What do I get when I put them together? Yeah, I get one of each, right? So it balances out. LiOH, all right? So that is the unbalanced equation. You take it from there, follow those same 4 steps that we've been talking about. You want to balance the equation. You want to convert to moles. You want to do the mole to mole relationship. And you want to take those moles to some other unit. All right, so follow them in order. Yes. I'm sorry, it's 6.941. So since we're kind of getting to the end, let's take a look at this one here, and let's see how we're doing. So first off, obviously here we have an equation. Is a balance? Is not balanced. So we want to balance it up. I'm going to throw some 2's at it and see what sticks. How about like a 2 there, maybe a 2 there, maybe a 2 there? Anybody agree with me? That's good. I feel good about that. By the way, if you did your table, you got your reactants, you got your products, you got your lithium, your hydrogen, and your oxygen here. Originally, we had 1 on that side, 1 on that side. We had 2 hydrogens and 3 hydrogens on the right. We had 1 oxygen and 1 oxygen. So really everything was balanced except for the hydrogen. And in this case, I personally, just so you know, I threw up a fraction there of 1/2 there to balance it. And that would give me 2 hydrogens on the right-hand side. And then I multiplied everybody by 2. So that's how I ended up with 2's everywhere along there. Yeah. I can. Let me try that. So if I, so this is a situation where, you know, we have just the hydrogen by itself, and we can go with a 1/2. Remember, we really need to turn this into a 2. So we need 1 there, and we have 1 on the other side. So the top number is what we need, and the bottom number matches this number. So if I do that, I have 1 lithium. I have hydrogen. 1/2 times 2 is 1. And 1 more on the right-hand side over here, which is 2. And now I still have 1 of those, but I can't leave it right as a fraction. So at this point, I need to multiply everybody by 2, and that will clear the fraction and give me whole numbers. And that's how we get to our, me throwing 2's everywhere on this page here. So let's do that. So we're gonna go back to 2. 2, when I take 1/2 times 2 gives me 1. And then I get end up with a 2 here. And then that should balance it out as 2 lithiums there, 2 there, 4 hydrogens there from here, and 2 hydrogens, and 2 is 4 there, and 2 oxygens there, and 2 oxygens there. Yeah, so now we're balanced. Yeah, good. You're welcome. Any other questions on that? All right, now we got the balance equation. We're ready to roll to step number 2, which is we're going to take whatever they gave us and convert it to moles. Do I need to do it in this case? What is the only number given to me? 5.32 moles of lithium. So do I need to convert it to moles? Yeah, don't unconvert it either, right? So that's done for us. So hey, step 2 is really flying right there. There, so that's done. So we have it now, 5.32 moles of lithium. It was already done for us, so there's no need to do it again. We're not really interested in lithium here. We're interested in hydrogen, right? So that is ultimately what we're trying to find. How many moles of hydrogen is what we're looking for. So we're ready for our third step, which is the stoichiometry step, the relationship between lithium and hydrogen. What is that relationship? How many moles of lithium? 2 moles of lithium gives me how many moles of hydrogen? 1 mole of hydrogen. This again is just the coefficients, the numbers in front. So just these guys right about there. Yeah. Any questions on that? That clearly gives me the 2 conversion factors that I could write for that if I wanted to, but I'm just going to kind of put it into the calculation if that's okay. So we're going to do step number 3 here. As step number 1 was done, we did, and step number 2 was already done for us. So in this case, I want to get rid of lithium and end up with hydrogen. So on the bottom should go the 2 moles of lithium. Up on top should be 1 mole of hydrogen. The moles of lithium is going to cancel, and that's going to be the stoichiometry. So we're going to divide that by 2, it looks like. Maybe if my calculator turns on. Divide by 2 here. That's going to give us 2.66 moles of H2 in this case. Do I need to do step number 4, which is convert the moles to some other unit? I do not, because I'm looking for moles. So I perhaps put a circle or a box around it and a happy face. 2 happy faces. I heart stoichiometry. Any questions on that? That's a really crappy heart, by the way. Yes. You do need to do quality. This is the stoichiometry from the equation right here. You do not have to do step number 2 where you take it from grams to moles because it was already in moles. So it's actually kind of good to go in that point as it's already in moles. So it's already in the correct units to do the stoichiometry part, which is step number 3. So it's a really good point.